Okay, so here is the PowerPoint that we were starting in class today. I was just going to briefly go through the first few slides that have the notes that just make sure you have all the correct answers on here. I really need you to fill these notes out by Monday, so if you're listening to this video, hopefully this will help you get that done. In your notes, number 1, it says, why aren't we crushed by the force of billions of air molecules that push constantly on the human body from all directions? Well, that is going to be this answer right here. Billions of molecules inside the body push outward just as hard. We're not crushed by the air pressure because our body is adjusted to it. We're accustomed to the air pushing on us from all directions, and that's just how our bodies are designed. So number 2 asks about why does air pressure exist? And that answer is going to be right here. Oops, right here. Number 2, air molecules take up space and have weight. That's quite simply why air pressure exists. Air pressure always decreases with increasing height. So that's number 3. That is an always thing. Number 4, at what altitude would you be above 50% of the atmosphere? 50% of the atmosphere shows up here, and that is going to be 3.5 miles above Earth's surface. I'm going to skip the 70 for just a moment, and then the 99.9% is in this bullet point. That happens about 30 miles. You can put 30.3 miles. 70% of the atmosphere is this one right here. At an elevation approaching the summit of Mount Everest, you would be above nearly 70% of all the air molecules in the atmosphere. Well, to find the summit of Mount Everest, unfortunately, we have to go back a slide. That is going to be here, where Mount Everest is right about 10 miles high. Or you could Google the height of Mount Everest and find out where that height is. So I'm going to guess somewhere right around 10 miles. So that would be my answer for the 70%, would be 10 miles. And number 5 asks for the average lapse rate. That is right here. Fairly linear relationship near the surface, but the lapse rate is going to be right about 3.5 to 3.6 degrees Fahrenheit for every 1,000-foot increase in altitude. It would be easiest really to consider it 3.5. It makes calculations a little bit simpler. So if we look here, the next question on the notes is this example right here. If the air temperature at the surface is 46 degrees Fahrenheit, what would the temperature be at 2,000 feet elevation? And at what elevation would the air temperature reach the freezing point of water? So in case you missed some of that discussion for your notes, let's go ahead and go through it here. All right, so for part A, we're starting at 46 degrees Fahrenheit, and we're going up 2,000 feet. Well, if it's 3.5 degrees Fahrenheit per 1,000-foot increase, then this would be 2 of those, so that's going to be 7 degrees Fahrenheit lower. So we'll take our 46, we'll subtract 7, and we'll end up there with about 39 degrees Fahrenheit for part A. Okay, then for part B, we're going to say, we're going to have to write ourselves a little linear equation. At what altitude or what elevation would the air temperature reach the freezing point of water? Well, if you consider that we have, like I said, it's a linear relationship. Linear relationships can be expressed here. Remember from Algebra 1, this B is your y-intercept. It's your starting point. That's going to be your 46 degrees. M is your slope or your rate. And that rate is going to be negative 3.5x. And y is going to be kind of your end. Oops, I'm not sure what I just did there. Oh dear. I just lost it. So y is going to be your ending point, and that's going to be the 32 degrees that we're looking for. So that's where we end up. To solve this equation, you're going to subtract 46 from each side. If I can do the math correctly this time, that would be super awesome. This ends up being negative 14, and that equals negative 3.5x. Then we can divide both sides by negative 3.5 to cancel this out. And this answer ends up being a positive 4. Well, remember, this is thousands of feet. So really, we are looking then at 4,000 feet altitude. And that's the answer to part B. Okay, next question on the notes is, what is the name for the condition where air temperature increases with height rather than decreases? That is a temperature inversion. That's right here. And that happens sometimes within the tropopause, and it'll happen in other layers. I'm sorry, within the troposphere, but it happens within other layers as well. So that's number 7. And number 8, where in the atmosphere does all the weather we are familiar with take place? That is going to be on this next slide here. The troposphere is the region of the atmosphere from the surface up to about 7 miles containing all of the weather we are familiar with. So there we go. That would be the troposphere for number 8. Number 9, where did the troposphere get its name? It came from a Greek word that means to turn or to change. And that is because the air, that's this guy right here, the air within the troposphere is always in motion. It's rising and descending. Those convection currents is where it gets its name. The air is turning or changing all the time. Okay, number 10, what indicates the top of the troposphere and transition into the stratosphere? That is here on this next slide. That's called the tropopause. This is number 10. And what indicates it is the isothermal zone, where the air temperature stops decreasing with height. And that's just above 11 kilometers. That's where that tropopause exists. So for number 10, I would say what indicates the top of the troposphere and transition into the stratosphere? I would say the isothermal zone at about 11 kilometers, and that boundary is called the tropopause. Number 11 is kind of where we left off in class, but it has a little bit of a confusing aspect to it. Nowhere on this slide does it mention the word latitude. It's sort of implied here in this bullet point. This is A, and then this is going to be B. I'm going to skip A for just a second because B is much easier to answer. With the seasons, we can see that the tropopause is higher in summer, lower in winter, so that's the answer to 11B. For 11A, we're talking about latitude. We need to remember where the latitudes are. This is going to come from previous earth science class and from science classes in middle school. You need to remember the equator occurs, its latitude is 0 degrees. And the poles are at 90 degrees north and south. So if we're talking about the tropopause being found at a higher altitude at 0 and decreasing as we travel poleward, then we could say as latitude increases, the height of the tropopause is going to decrease. So that's going to be our answer for 11A. As latitude increases, the height of the tropopause will decrease. Number 12. I'd kind of like you to think about this on your own for just a little bit. It asks you, why do you think very little water vapor exists in the atmosphere above the tropopause? And I'm going to ask you to go ahead and answer number 12 on your own. I'm not going to give you the answer to it here in the notes. I would like you to think about that on your own and see what you can tell me on Monday. And I will go over it with you at that point after you've had a bit to construct an answer on your own. So that concludes the first part of these notes, and I will flip my notes page over and we can continue on the back here in the next video. Thank you.